Okay, so let's do this problem. So we have, for the boundary value problem, y double prime minus q of xy equals minus lambda y with Dirichlet conditions, and where q of x is greater than or equal to a, show that all eigenvalues are bounded below. So a could be minus a million, so note that a can be negative. Also, this problem is pretty tricky. Think it through, but if you can't, but if you can solve it for a greater than 0, then you're good. So what I mean here is, it's very likely that you will see a problem very similar to this, but with this additional assumption that a is greater than or equal to 0. Okay, but I'm going to do it for maybe I'll do it both ways. Maybe I'll just assume that a is greater than or equal to 0, and then I'll show how to modify it to get it to work for a simply greater than or equal to a. Okay, so first, that's how I'm going to do it. So first, we'll assume that a is greater than or equal to 0. Okay, if phi is an eigen function with eigenvalue. Okay, so I think what I'm going to do, I'm just going to go straight to the Rayleigh quotient. So let me go back to that. Instead of basically just kind of re-deriving it each time and having to deal with all of these, various things if lambda is equal to 0, not equal to 0, let me just find it. Whoops. This is it. So this is the Rayleigh quotient, and we're just going to show something about the Rayleigh quotient. We want to show the Rayleigh quotient is bounded below. Where am I here? Okay. Okay. We examine but actually, you know what? I'm not going to do that. I'm sorry. I keep going back and forth. Just do this. You should try to do this using the Rayleigh quotient. It's morally equivalent. I mean, it's the same thing as what I'm going to do, but the way I'm about to do it is kind of a little more straightforward, a little more how I would expect you to do it on the test. But the Rayleigh quotient would also be fine. Okay, it's an eigenfunction with eigenvalue lambda. That is phi double prime minus q is equal to minus q. Phi is equal to minus lambda phi, and it satisfies the boundary conditions. Then, very familiar computation, the integral from 0 to 1, algin. There we go. The integral from 0 to 1 of phi squared is equal to, once again, let's see if I, phi is equal to minus 1 over lambda times this. So it's going to be minus frac 1, lambda. We're going to have the integral 0, to 1. Okay, and then we're going to have phi double prime minus q, minus q phi, I've got that, okay, and then times phi. Okay, so now what we're going to have happen, we're going to have this, and we're going to do a little integration by parts. So we're going to have the boundary terms. Now, notice the boundary terms are 0. So I'm going to have the boundary terms. So I need to be careful when I say integration by parts. So I've got phi double prime times phi. I'm going to do integration by parts on that. but leave the q phi times phi alone. So I'm going to do integration by parts on phi double prime times phi. The boundary terms are going to be phi prime times phi, but phi of 0 and phi of 1, or sorry, phi of 0 and phi of pi are both equal to 0, so we won't have those. Now I just realized this integral should be up to pi, not to 1. Okay. So this is going to be 1 over lambda, and we're going to have the integral going from 0 to pi. Now notice what's going to happen. When you do the integration by parts with the phi double prime times phi, you're going to get minus phi prime. You're going to minus that squared. But you're going to have you're going to keep the q. So then it's going to be, so phi double prime times phi. You do integration by parts, take one of the derivatives from the phi double prime and put it onto the phi, but then you still have the minus q phi prime squared like this, because you didn't do integration by parts on that term. Okay, so now we've got this minus sign here, and this is going to be equal to 1 over lambda. We distribute the minus sign, and we're just going to get this, but without the minus sign. It's just going to be this. Okay. So what's happening here? Well, with a plus. What do we know is going on here? The left-hand side, the left-hand side of this is positive. Well, I'm going to just leave it like this. Left-hand side is positive since it is integrating a non-negative function. It can't be 0, otherwise the eigenfunction would be identically equal to 0, but this isn't allowed. So it's got to be positive. So therefore the right-hand side is positive. The integral on the right-hand side is non-negative. The integral on the right-hand side is non-negative and can't be 0, since then the right-hand side is 0, but the left-hand side is positive. Okay, so what it means is that the integral is positive, so then 1 over lambda is greater than 0, whence lambda is greater than 0. Okay, so we'll first assume, okay, with eigenvalue lambda not equal to 0, then this is true. Okay, so what we've shown is that if lambda is not equal to 0, lambda has to be positive. Well, if lambda is equal to 0, lambda could be equal to 0, but it's still bounded below. So therefore, okay, so the logic here is, let's assume that lambda is not equal to 0. If lambda is not equal to 0, it means lambda is positive. Therefore, lambda can't be negative. Therefore, lambda is greater than or equal to 0. Okay, now this uses the fact the left-hand side is positive. The integral on the right-hand side is not negative. Let me actually explain why that is. The integral on the right-hand side is not negative since q is greater than or equal to 0. And so it is the integral of a non-negative function. So we're using the fact that q is greater than or equal to 0 for this to work. But let's see what happens. Now let's assume, next we show how to modify this for when we only know that q is greater than or equal to some a. We still have the same computations. everything's going to be the same. This is going to be equal to this. So this is still going to be the same. Let's see how many times I messed up. Not too many times. Wow. Okay, so we still have this. This is all true. The only difference now is that we don't know about q phi squared. So we don't know about q phi squared. So what we're going to do, q phi squared could be like q could be negative. This integral here could be negative. In which case, what does it directly tell us about lambda? So here's what we're going to do. We're going to rearrange this and basically get the Rayleigh quotient. So in the denominator, we're going to have this. And then in the numerator, we're going to have this. Like that. Okay, let's see how that looks. Okay. Not quite, because I don't want that lambda there, do I? Okay. So this is what we have. Okay. Okay. And it's actually good that I didn't copy and paste the Rayleigh quotient, because here I've got minus q, whereas before in the standard way this is set up with plus q. Anyways, there's a reason that I have minus q instead of for what we've been doing and for the textbook. It does it with a plus q, but everybody else does it with a minus q and a. Anyways, okay. Never mind. You know what? Forget about it. I don't know why I'm feeling the need to say all that. Okay, so now what we're going to do is this. What do we know about q? We know q is greater than a. So this is going to be greater than or equal to a. This is going to be greater than or equal to this. But in a here, let's see what we get when we do that. And now notice what we're going to have happen. The integral from, and maybe I'll just do this explicitly. We're going to have this. So this a integral phi squared over phi squared, that's going to be equal to a. And so this is going to be equal to the following. I'm going to change this a little bit, so it'll be this. I'm not going to have this part plus a. Whoops. Plus a. Whoops. Plus a. So that's what we get. So now we just need to show that this has a lower bound. Well, we're going to do something very similar to what we did in this problem up here. So the integral, so first, is going to be a little more complicated though. So now, next, okay, if we think about phi squared, phi of x is going to be equal to phi of x minus phi of 0. Why is that? Well, phi of 0 is equal to 0. So nothing going on there. And now by the fundamental theorem of calculus, this is the integral from 0 to x. I'm going to use my dummy variable of y, dy. And now, again, this is going to be another instance of the Cauchy-Schwarz or a Jensen's inequality. This is going to be less than or equal to. This is going to be less than or equal to. And if you don't know what the Jensen's inequality is or Cauchy-Schwarz inequality, that's completely fine. You are not going to have to do this for the exam, but for those of you who are interested, I want to show you. This is one of the reasons this problem is tricky. Okay, so now we're going to have this. And now we're going to square this. Okay. And now what we're going to get is that, yeah, that's right. So this is going to be less than or equal to. Okay, so what is this going to be less than or equal to? Well, square root of x. So I'm not going to get the most what am I trying to say here? The most efficient inequality, or the best inequality. Square root of x is less than or equal to the square root of pi, because x only goes from 0 to pi, like that. And then this right here, this is going to be less than or equal to this integral from 0 to pi, like that. So now what this says is the phi of x is going to be less than or equal to the square root of pi times the square root of this. Okay, now there's a number of ways that we can proceed here. Notice I'm going to explain this slightly a little different than I did in the previous problem. Notice if I start with absolute values, like here, I've got the absolute value of phi of x, well, is equal to this. And by the fundamental theorem of calculus, I can just keep the absolute value on the outside here, like that. And now I don't need absolute values anymore because this is a positive thing there. So what this tells me is that the absolute value of phi of x is equal to that. Sorry, less than or equal to that. Okay, so this phi of x squared, this is going to be less than or equal to pi times this integral. Okay, so if we integrate this, from x equals 0 to x equals pi, to x equals pi, we get the following, the integral from 0 to pi. This is going to be less than or equal to, okay, so now we're integrating this with respect to x from 0 to pi. Well, this is a constant as far as x is concerned, so we're just going to get pi squared times this. And now we can rearrange this, so if we divide both sides by the integral of phi squared and divide both sides by pi squared, what we get is that this, and now I'm going to get rid of the argument because the argument is not important now. It's just going to make things a little more confusing. Okay, so this divided by this, so is going to be greater than 1 over pi squared. Thus, the thing that we started with was, lambda that's the thing that we started with. Thus, lambda is going to be greater than 1 over pi squared plus a. Okay, so all of the eigenvalues are bounded below by 1 over pi squared plus a. Okay, and again, like I said, in the problem here, I think I said it was tricky. This problem is pretty tricky. This first part here, you will be expected to do that, or you should be expected to do that. That is a totally legitimate problem for me to have on the exam to prove that. We've done several things like that throughout the semester, and I'm telling you right here. Now, for this part right here, modify this for when q is greater than or equal to a, and a might be a negative number. that part is beyond what I would expect you to be able to do on the exam. But it's interesting and uses this very like fundamental inequality called a Poincare inequality, which is this inequality right here, and we used it up here in the previous problem as well. Okay, that's all I got for today. Or not for today, but for this problem.